Hi, everyone. You join me on a very special occasion. This is part two of our interview series with Jim Keller. He is currently CTO of a new AI company called Tenstorrent, but in the past, he's worked at DEC, Apple, AMD, Intel, Broadcom, Cybyte, Tesla. Jim, am I missing anything there?
I worked at AMD twice,
Oh, yes, that's true.
so I don't know what to make of that.
I think I have a couple of questions for you about that. It's I want to actually let's start with that. That's a good place to start, right? It's a lot of my audience at least know you from your work at AMD on the Zen, the Skybridge platform, and now AMD's gaining market share with their product line, and you're off onto bigger and better things. But there's been a lot of confusion as to your exact role at AMD during that project. Some people believe you're integral in nailing down Zen, Zen 2, Zen 3, high level microarchitecture. Others believe you put people in place, signed off at high level, then focused on the ARM version, the Skybridge K12. So, can you give any clarity as to your role there? How deep you went with Zen versus K12, or your involvement in things like Infinity Fabric?
Yeah, it's well, it was a complicated project, right? Because AMD, when I joined, they had Bulldozer and Jaguar, and they both had some charming features, but they weren't successful in the market, and the roadmaps weren't aggressive. They were falling behind Intel, and so that's not a good thing to do. If you're already behind, then you better be catching up, not falling behind. So I took the role. I was president of the CPU team, which I think when I joined was 500 people. And then over the next 3 years, the SoC team, the fabric team, some IP teams joined my little gang. And I think when I left, it was 2,400 people, I was told. So I was a VP with, a staff, right? So I had senior directors reporting to me and senior fellows. And my staff was like 15 people. So I was hardly writing RTL. So that said, um, but we had a whole bunch of things. So like I'm a computer architect, not really a manager. Um, I wanted the management role, which was the biggest management role I'd had at the time. I'd been the VP of a startup, but that was 50 people, and we all got along, and so this was a fairly different play for me. But I knew that the technical changes we had to make would be involved in getting people aligned to it. And I didn't want to be the architect on the side arguing with the VP about why somebody could or couldn't do the job or why this was the right or wrong decision. So Mark Papermaster, I told him my theory, and he said, "Okay, we'll give it a try." And it worked pretty good because then I had, let's say, direct authority, as it were. But people don't really do what they're told to do, right? They do what they're inspired to do, right? And so you have to lay out a plan, and part of it was finding out like who are the right people, to do different things. And sometimes somebody's really good, but their ideas, like people get very invested in what they did last time, or they believe things can't be changed. And I would say my view was things were so bad that almost everything had to change. And so I went in with that as like a default thing. Does that make sense? Now, it wasn't that we didn't find a whole bunch of stuff that was good to use, but you had to prove that the old thing was good as opposed to prove the new thing was good. So we changed that mindset. Architecturally, I had a pretty good idea what I wanted to build and why. And I found people inside the company, Mike Clark, Leslie Barnes, Jay Fleischman, there are quite a few, Debjet. There's quite a few really great people that once we described what we wanted to do, they're like, yeah, we want to do that. And like architecturally, I had some input. There was often decisions, analysis. People had different opinions. I was fairly hands-on doing that, but again, I wasn't doing block diagrams or writing RTL. And we had multiple projects going on. With Zen, there was the ARM cousin of that, the follow-on that integrated them both. There was some new SoC methodology, but we we did more than just CPU design. We did methodology design, IP refactoring, uh, very large organizational changes, and I was like hands on top to bottom with all that stuff. Does that make sense?
Sure. It's a few people consider you the father of Zen. Do you think you ascribe to that position, or should
Uh,
that go to somebody else?
yeah, or one of the uncles. It's hard to say.
Distant
There
relative.
was a lot of really great people on Zen. So, and it was built. There was a methodology team that was worldwide. The SoC team was partly in Austin and partly in India. The floating point and cache was done in Colorado. The core execution front end was in Austin. The ARM front end was in Sunnyvale. We had good technical leaders. I was in daily communication for a while with Suzanne and Steve Hale, who kind of built the front end of the Zen core and the Colorado team. So, like, there was some really good people. Mike Clark's a great architect. Yeah, so we had a lot of fun. And success has a lot of authors, failures has one. So that was the success. And then some other teams stepped up. We moved Excavator to the Boston team, where they took over the finishing, the design, and the physical stuff. Harry Fair and his guys did a great job on that. So there was some fairly stressful organizational changes that we did going through that, and the team all came together. So yeah, I think there was a lot of camaraderie in it. So I won't claim to be I was the instigator and the chief nudge, and part architect, part it's a transformational leader, and so it was fun.
Was
So
everything that you did during
a
that
couple
time,
funny
has
things
that...
happened during it. So,
Sorry, go
sorry,
on.
go ahead. No, there's a little bit of a lag between here and
Yeah.
whatever country you're
It's
in right now.
I was going to say, is everything that you worked on now out at AMD, or is there still, kind of roadmap stuff still to come out, do you think, from the ideas that you helped propagate?
Um, so when you build a new computer, and Zen was a new computer, there was already work underway on what they called SOC 15, which is the new fabric and bus. Um, you build in basically a roadmap, right?
Yeah.
So I was thinking about, what are we going to do for 5 years, like chip after chip, and we did this at Apple too. When we built the first big core at Apple, we built big bones, right? So you can't, when you make a computer faster, there's two ways to do it. You make the fundamental structure bigger, or you tweak features. And Zen had a big structure. And then there was obvious things to do for several generations to follow up. And they've been following through on that. So at some point you'll have to do another big, rewrite and change. I don't know if they've started that yet. What we had planned for architectural performance improvements were fairly large over a couple of years, and they seem to be doing a great job at executing to that. But yeah, I've been out of there for a while, 4 or 5 years.
Yeah.
So
Yeah, it's. I think they said that Zen 3, the last one that just came out, was a rewrite. So I think some people are thinking that was still under your direction.
yeah, it's hard to say. Like even when we did Zen, like we did a from scratch design, clean design at the top. But then when they built it, there was a whole bunch of pieces of RTL that came from Bulldozer and Jaguar, which were perfectly good. They just had to be modified and built into the new Zen structure. So hardware guys are super good at reusing code when it suits them. And so when they say they did a big rewrite, they probably took some pieces and, re-architected them at the top. But when they built the code, it wouldn't surprise me if somewhere between 20 and 80% of the code was the same stuff or mildly modified. But that's pretty normal. The key is to get the structure right and then reuse code as needed, as opposed to taking something that's complicated and trying to tweak it to get somewhere. So if they did a rewrite, they probably meant they fixed the structure.
So I mean, moving on from that, you're several companies on. You're now at a company called Tenstorrent. with an old friend, Ljubisa Bajic.
Uh-huh.
But you've been jumping from company to company to company, for basically your whole career. You're always finding another project, another opportunity, another angle. Not to be too blunt, but
Well,
is Tenstorrent going to be a
yeah.
forever home?
Well, first, I was at Digital for 15 years, right?
You
Now,
are that.
it
That's
was
true.
two different careers because I was in the mid-range group where we built computers out of ECL, and they were refrigerator-sized boxes. And I was in the alpha team where we built little microprocessors, little teeny things, right? Which at the time we thought were huge, 300 square millimeters at 50 watts. Just blew everybody's mind. And so I was there for a while. I went to AMD right during the internet rush, and we did a whole bunch of stuff in a couple of years. We started Opteron, hypertransport, 2P servers. Like, it was kind of a whirlwind of a place. But I got sucked up, or caught up in the enthusiasm of the internet, and I went to SciByte, which got bought by Broadcom, and I was there for 4 years total. And we delivered several generations of products, and I was at PA Semi, and we delivered a great product, um, but they didn't really want to sell the product for some reason, or they thought they were going to sell it to Apple. So I actually went to Apple, and then Apple bought PA Semi, and then I worked with that team. So I was, between PA Semi and Apple, that was 7 years. So I don't really feel like that was jumping around too much. Then I jumped to AMD, I guess, and that was fun for a while. And then I went to Tesla, where we delivered Hardware 3. So that was, kind of phenomenal standing start to driving a car in 18 months. I don't think that's ever been done before. And that product shipped really successfully. They built 1 million of them last year, Tesla. And then, Intel was a different kind of whirlwind. So, you could say I jumped in and jumped out, but I sure had a lot of fun at Intel. Um, so, so yeah, I've been around a little bit. I like to think I mostly get done what I set out to accomplish. My success rate there is pretty high in terms of delivering products that have lasting value. I'm not the guy to tweak things in production. I like either a clean piece of paper or a complete disaster. You know, that seems to be the things I do best at. It's good to know yourself. I'm not an operational manager. Um, so Tenstorrent is more the clean piece of paper. AI space is exploding. The company itself is already many years old, but we're building a new generation of parts and going to market and starting to sell stuff. And I'm CTO and president. I have a big stake in the company, both financially and also, I say, commitment wise to my friends there. So I plan on being here for a while.
But that sounds good. If I can just cycle back one, I know it's still kind of fresh, so I'm not sure what kind of NDAs you're still under. Um, but your work at Intel, was that more sort of a clean slate, or can you sort of go into any detail about what you did there? Beyond the sort of PR stuff that we've all heard.
I can't talk too much, obviously. The role I had was senior vice president of Silicon Engineering Group, and the team was 10,000 people. So they're doing so many different things. It's just amazing. It was something like 60 or 70 SoCs in flight at the time, literally, from design to prototyping, debugging, production. So it was a fairly diverse group, and there my staff was vice presidents and senior fellows. So it was a big organizational thing. Um, I had thought I was going there because there was a bunch of new technology to go build. I spent most of my time working with the team about both organizational and methodology transformation, like new CAD tools, new methodologies, new ways to build chips. A couple of years before I joined, they started what's called the, SoC IP view of building chips versus Intel's historic monolithic view. And that, to be honest, wasn't going well because they took the monolithic chips, like they built great client and server parts, and broke it into pieces. But you can't just break it into pieces. You have
Yeah.
to actually rebuild those pieces, and some of the methodology goes with it. And yeah, we found a bunch of people who were really excited about working on that. And, I spent a lot of time on, quality, IP quality, density, libraries, characterization, process technology, like you name it. It was
Mm.
my my days were kind of wild. Like some days I'd have 14 different meetings in one day. It would just be click, 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 because there's so many things going on.
All those meetings, how did you get anything done?
I don't get anything done. Like I told you, I was a senior vice president. It's like evaluation, set direction, make judgment calls. Let's say drive some organizational change, people change, and that adds up after a while. The key thing about getting somewhere is knowing where you're going, and then putting an organization in place that knows how to do that, and that takes a lot of work. Yeah, so I didn't write much code, but I did send a lot of text messages.
That kind of code, right? I
Yeah,
mean,
that kind of code.
Intel now has a new sort of engineering focused CEO in Pat Gelsinger. Would you ever consider going back if the right opportunity came up?
I don't know. I have a really fun job and a really explosive growth market. So I wish him the best. I think it was a good choice. I hope it's a good choice. We'll see what happens. He definitely cares a lot about Intel, and he's had real success in the past. So he's definitely going to bring a lot more technical focus to the company. Um, but I like working with Bob Swan just fine. So he was, you know, we'll see what happens.
I mean, if I go through your career, it's you've kind of gone between high performance computing and low powered efficient computing, and now you're in this sort of world of need for AI acceleration.
Mm-hmm.
Has it ever got boring?
No, no, it's really weird. Well, it's changed. It's changed so much, and at some level, it doesn't change at all. Like computers at the bottom, they just you add ones and zeros together. It's like it's pretty easy. 0, 1, 1, 0, 1, 1, 1, 0, 0. It's not that complicated. But I worked on the VAX 8800 where we built it out of gate arrays that had 200 OR gates in each chip, like 200, right? And now at Tenstorrent, like our little computers, we call them tensor cores, are 4 trillion operations a second per core, and there's 100 of them. So like the building block shifted from 200 gates to 4 teraops. So that's kind of a wild transformation. And then the tools are way better than they used to be. Like what you can do now, like you can't build more complicated things unless the abstraction levels change and the tools change. And there's been so many changes on that kind of stuff. And when I was a kid, I used to think I had to do everything myself, and I worked like a maniac and coded all the time. And now I know how to work with people and organizations and listen, stuff like that. People skills. Like I probably get a pretty uneven scorecard on the people skills, but um, I do have a few, and that's interesting too.
Would you say that engineers need more people skills these days? Because everything's
Mm,
complex, everything's got separate abstract layers, and if you want to work between them, and
nah, no. So here's the fundamental truth: people aren't getting any smarter, right? So people can't work across more things. That's dumb, right? You do have to build tools and organizations that support people's ability to do complicated things, right? So like it's interesting. The VAX 8800 team was like 150 people, and the team that built first processor at Apple, Hurricane, that was in the A, well, the first big processor. I guess the second custom Apple core was 150 people. Now, the CAD tools were unbelievably better. We used thousands of computers to do simulations. We had tools that could place and route 2 million gates versus 200. So some things changed radically, but the number of people an engineer talked to in a given day didn't change at all. Like if you have an engineer talk to more than 5 people a day, they'll lose their minds. So, some things are really constant.
in terms of that constant idea, you've spoken about um, CPU instruction sets in the past. And one of the biggest requests for this interview I got was around your opinion about CPU instruction sets. Specifically how we deal with fundamental limits on them, how we pivot to better ones, and what's your skin in the game in terms of, ARM versus x86 versus RISC-V? I think at one point you said most compute happens on a couple of dozen opcodes, so ISA doesn't matter.
Yeah,
Am I
yeah, yeah.
remembering that correctly?
It's a very sad story. Yeah, 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 yeah. No, it's not even a couple of dozen. 80% of the execution is like 6 instructions. Load, store, add, subtract, compare, and branch. You pretty much covered it. If you're writing in, Perl or something, maybe call and return are more important than compare and branch. But you know, instruction sets only matter a little bit, right? You can lose 10 or 20% because you're missing instructions, or for a while we thought variable length instructions were really hard to decode, but we keep figuring out how to do that. You basically predict where all the instructions are in tables, and once you have good predictors, you can predict that stuff well enough. So fixed length instructions seem really nice when you're building little baby computers, but if you're building like a really big computer, the predictor to figure out where all the instructions are isn't dominating the die. So it doesn't matter that much. And when RISC first came out, an x86 was half microcode. So if you look at the die, half that chip was a ROM, or maybe a third or something. And the RISC guys could say there's no ROM in a RISC chip, so we get more performance. But now the ROM is so small you can't find it. Actually, the adder is so small you can hardly find it. Right? So what limits computer performance is predictability. And the two big ones are, instruction predictability and branch predictability and data locality. And now the new predictors are really good at that. They're big. Like the predictors are way bigger than the adder. Right. And that's where you get into the CPU versus like GPU or AI engine debate.
Yeah.
Like the GPU guys will say, look, there's no branch predictor because we do everything in parallel. So the chip is way more adders and subtractors. And that's true if that's the problem you have, but they're crap at running C programs.
Yeah, it's all about crafting the software at the compile time, right?
Yeah.
If you can do that well, then
GPUs were built to run shader programs on pixels. So you're given like 8 million pixels. And so, the big GPUs now have 6,000 threads. So you can cover all the pixels with each one of them running, 1,000 programs per frame. But it's sort of like, an army of ants carrying around grains of sand. Whereas big AI computers, they have really big matrix multipliers and like a much smaller number of threads, essentially, that do a lot more math because the problem is inherently big. Whereas the shader problem was the problems were inherently small because there were so many pixels. So there's genuinely three different kinds of computers: CPUs, GPUs, and AI. And then NVIDIA is kind of doing the tweener thing where they're using a GPU to run AI and they're trying to enhance it. And some of that's obviously working pretty well, and some of it's obviously fairly complicated. And so it's an interesting, and this happens a lot. Like general purpose CPUs, when they saw the vector performance of GPUs, added vector units, and sometimes that was great because you only had a little bit of vector computing to do. But if you had a lot, GPU might be a better solution.
I think you've said before that going beyond the sort of matrix, you end up with sort of massive graph structures, especially for AI and ML. And the whole point about Tenstorrent is it's a graph compiler and a graph compute engine, not just a simple matrix multiply.
Yep. Yeah. So there's from old math. I'm not a mathematician, so mathematicians are going to cringe a little bit, but there was scalar math like A equal B plus C times D. Right. And when you had a small number of transistors, that's all the math you could do.
Yeah.
And then we got more transistors, and you could say, hey, I can do a vector of those, like an equation properly in a step. And then we got more transistors, we could do a matrix, like multiply, right? And then as we got more transistors, you sort of wanted to take those big operations and break them up, because if you make your matrix multiplier too big, the power of just getting across it's a waste of energy. So you find you want to build this optimal size block. It's not too small like a thread in a GPU, but it's not too big like covering the whole chip with one matrix multiplier would be a really dumb idea from a power idea. So then you get this array of medium-sized processors, where medium is something like 4 teraops, like that's, which is hilarious to me, by the way, because I remember when that was a really big number. And once you break that up, now you have to take the big operations and map them to the array of processors. And AI looks like a graph of very big operations. It's still a graph. And then the big operations are factored down into smaller graphs. Now you got to lay that out on a chip with lots of processors and have the data flow around it. And that seems to be a very different kind of computing than running a vector or matrix program. So let's call it, scalar, vector, matrix. Raj and I used to call it spatial. I would say graph would probably be a better word.
And then, correct me if I'm wrong, but you're putting in vector engines into your graph core next gen. So it's
We're
becoming
putting in
this.
general purpose CPUs that have vector engines on them.
Yeah.
And that turns out to be, when you're running AI programs, there's some general purpose computing you just want. And then there's sometimes in the graph where you want to run a C program on the result of an AI operation. And having that stuff be tightly coupled is nice. Actually, on the same chip, so the latency is super low and the power to get back and forth is reasonable. So yeah, we're working on an interesting roadmap for that. And by the way, that's a little computer architecture research area. Like, what's the right? Everybody always has this idea. What's the right mix with, accelerated computing and general purpose computing, and how are people using it, and how do you build it in a way programmers can actually use it? Right. That's the trick, which we're working on.
So many people are asking, what do you think about ARM versus x86? Which one has the legs? Which one, has the performance? Do you care much? Or
I care a little. Like, here's what happened. So when x86 first came out, it was super simple and clean, right?
Mm.
And then at the time, there was multiple 8-bit architectures, x86, the 6800, 6502. I programmed probably all of them way back in the day. And then x86, oddly enough, was the open version, right? They licensed that to 7 different companies. And then that gave people opportunity to put in tape. But Intel, surprisingly, was both licensed it in one long run. But then they went to 16 bits and 32 bits, and then they added virtual memory, virtualization, security, 64 bits, and then more features. So what happens to an architecture is as you add stuff, you keep the old stuff so it's compatible. So when ARM first came out, it was a clean 32-bit computer. And compared to x86, it just looked like, way simpler and easier to build. But then they added a 16-bit mode and the IT instruction, which is awful, and a kind of a weird floating point vector extension set with overlays in a register file, and then 64 bits, which partly cleaned it up. And they added, there was some special stuff for security and booting, and so it slowly got more complicated. Now RISC-V shows up, and it's the shiny new cousin, right? Because there's no legacy, and it's actually an open instruction set architecture, and people build it in universities where they didn't have time or interest to add too much junk, like some architectures have. So, relatively speaking, just because of its pedigree and age, it's early in the life cycle of complexity, and it's a pretty good instruction set. They did a fine job. So if I was just going to say, I want to build a computer really fast today, and I want it to go fast, RISC-V is the easiest one. It's the simplest one. It's got all the right features. It's got the right top 8 instructions, that you actually need to optimize. It doesn't have too much junk. So, yeah.
So modern instruction sets have too much bloat, especially the old ones, because they've
Well,
got too much
no.
legacy baggage.
Instruction sets that have been iterated and added to will have too much bloat.
Yeah.
That's what always happens, right? So as you keep adding things, like, the engineers have this struggle, right? You have this really good design, and there's 10 features, so you add some features to it. The features all make it better, but they make it more complicated. And as you go along, every new feature you add gets harder to do because the interactions with that feature and everything else gets terrible. And the marketing guys and the old customers will say, don't delete anything. But meanwhile, they're all playing with the new fresh thing that's
Mm.
only does 70% of what the old one does, but it does it way better because it doesn't have all these problems. Right. So this is, I've talked about diminishing return curves. There's a bunch of reasons for diminishing returns, but one of them is the complexity of the interactions of things slow you down to the point where something simpler that did less would actually be faster. And that's happened many times. It's some
Mm.
result of complexity theory and human nefariousness, I think.
So, do you ever see a situation where x86 gets broken down and something just gets reinvented, or will it just remain sort of legacy and then just new things will pop up like RISC-V too?
Well, Zen was a fairly clean slate. It obviously had to carry along baggage for this and
Mm.
that, but they deprecated a lot of the old 16-bit modes and bats, and
Mm.
there's a whole bunch of junk that disappeared. And sometimes, if you're careful, you can say, all right, I need to support this legacy, but it doesn't have to be performant, and I can isolate it from the
Mm.
rest of the design.
Emulate it and
So
stuff.
yeah, emulate
Yeah.
it or support it. And we used to build computers such, that you had a front end, fetch, dispatch, execute, load, store, L2 cache. And if you looked at the boundaries between them, you'd see like 100 wires doing random things that were dependent on exactly what cycle of the, or what phase of the clock it was. Now the interfaces tend to look just like instruction boundaries. I send an instruction from here to there, and then I have a protocol that says act. So the computer inside doesn't look like a big mess of stuff connected together. It looks like 8 computers hooked together that do different things. There's the fetch computer and the dispatch computer and the integer execution computer and the floating point computer. And if you do that properly, you can change the floating point without touching anybody else. And again, that's less of an instruction set thing than what was your design principle when you build it, and then how did you do it, and were you faithful to that? Because the thing is, you get to a problem, you say, boy, if I could just add these 5 wires between these 2 boxes, I could get rid of this problem. But every time you do that, every time you violate the abstraction layer, you've created a problem for future Jim, right?
Future Jim
like
is.
like I've done that so many times. It's like if you'd solved it properly, it would still be clean. But at some point you always have to hack a little bit, and then that over time that kills you. So
I've seen a number of talks where you speak about the concept of abstraction layers in pretty much a lot of aspects of engineering, but also kind of life as well, so that you can independently upgrade different layers without affecting those above and below, and providing new platforms to build upon. What point in your life did that kind of ethos click, and
hmm.
what happened in your life to make that that be a pervasive element of your personality?
Oh, pervasive element of my personality. That's pretty funny. I know I repeat it a lot. Maybe I'm trying to convince myself. Um, the like when we built EV6, so Dirk Meyer was the other architect, and then we had a couple other strong people. Um, we divided the design into a few pieces. We wrote a very simple performance model that got it. But when we built the thing, it was a relatively short pipe for an out of order machine because we're still a little weak on predictors. And there was a lot of interactions between things. And it was a difficult design to build. And we also built it with, at the time, Digital had a custom design methodology. So we had 22 different flip flops. Like people could roll their own flip flop, and we frequently would build large structures out of transistors. And I remember somebody asked me what elements were in our library, and I said both of them, N devices and P devices, right? And then I went to AMD, and K7 was built with a cell library. Now the engineers were really good at laying down the cell libraries in a way that got good performance, but they only had 2 flip flops, a big one and a little one, and they had a clean cell library. So they had an abstraction layer between the transistors and the designers. And this was before the age of really good place and route tools. And that was way better. And then the interface that we built on EV6, which was later called the S2K bus, because we licensed it to AMD, had a lot of complicated transactions to do snoops and loads and stores and reads and writes and all kinds of stuff. And a friend of mine who was at Digital Research Lab I explained how it worked to him one day. His name is Kurosh Gratzlu. He went to Google later and became one of their security gurus. Like he listened to me and he said, he just shook his head. He's like, Jim, that's not the way you do this. And he explained how virtual channels worked and how you could have separate abstract channels of information, right? And you get that right before you start encoding commands and saying what a wire does when it wiggled. So the result of that, let's say, educational seminar slash ass kicking was hypertransport, which had a lot of the protocol of the S2K bus, but it was built in a much more abstract way. So I would say that was probably, my move from AMD to or digital to AMD, where we had the ideas of how to build high performance computing, but the methodologies were, like, say, integrated. Like transistor up to architecture was literally could be the same person.
Yeah.
And at AMD, there was architects, micro architects. The RTL people write Verilog, but they literally translated it to gates and the gate library people. It was much more of a layered approach. And K7 was quite a fast processor. And our first swing at K8, we kind of went backwards because Bruce Gieske was my favorite circuit partner at the time. He and I could talk about big designs, but we solved as transistors. But that's a complicated way to build computers. And since then, I've been more convinced, like, the abstraction layers are right. You don't overstep human capability. That's the biggest problem, right? If you want to build something bigger and more complicated, you better solve the abstraction layers because people aren't smarter. And if you put more than 100 people on it, it'll slow down, not speed up. And so you have to solve that problem.
If you have more than 100 people, you need to split it into 2 abstraction layers. Maybe.
Yeah, exactly. And there's reasons for that. Like human beings are really good at tracking, your inner circle of friends is like 10, 20 people. It's like a close family, right? And then there's this kind of 50 to 100, depending on how it's organized, that you can keep track of. But above that, you read everybody outside your group of 100 people as semi-strangers. And so there you have to have some different contract about how you do it. Like when we built Zen, we had 200 people, and half the team did the front end and half the team did the back end. And the interface between them was defined, and they didn't really have to talk to each other about the details behind the contract, right? And that was important. Now, they got along pretty good and they worked together, but they didn't constantly have to go back and forth across that boundary.
Speaking about abstraction layers, you've said on stage in interviews in the past that you're not worried about Moore's law. The process node side, evolution of semiconductors will, eventually get worked out by someone somewhere. Would you say that your attitude towards Moore's law is apathetic, or do you draw or trust engineers that will work it out?
Super proactive. Yeah, still, like, yeah, that's not apathetic at all. Like, I know a lot of details about it. Well, you get into these kind of, people conflate a few things. Like Intel's 10 nanometer slipped, right? And people said, oh, that's because Moore's law is dead. But TSMC roadmap didn't slip at all, right? Now, some of that was alignment, right? TSMC's roadmap aligned to the EUV machine availability. So when they went from 16 to 10 to 7, they did something, and TSMC has been really good at kind of doing these half steps. So they did 7 without EUV, and then 7 plus with EUV, and then 5 with more, and then 5 plus they tweaked stuff. And then and the UV machines, for a while, people weren't sure if they were going to work. But now ASML's market cap's twice Intel's. So, and then there's a funny thing. I realized that the locus of innovation, like we tend to think of TSMC, Samsung, Intel as the process leaders, but a lot of the leadership is actually in the equipment manufacturers, Applied Materials, ASML. So who's building the innovative stuff? And EUV machines, the worldwide sales. So the number, something like TSMC is going to bought like 150 EUV machines by 2023 or something like that. Like the numbers are phenomenal because not too many years ago, people weren't even sure they're going to work. And now there's X-ray lithography coming up. And again, you can say, well, it's impossible, but bloody everything has been impossible. Um, and then, the fine print. This is a Richard Feynman, sentence. He was kind of smart. He said there's lots of room at the bottom, and I personally can count. And if you look at how many transistors, how many atoms are across transistors, there's a lot, right? And how many transistors you actually need to make a junction without too many quantum effects is only 10. So, there's lots of room there.
It's I recently put out a video about IBM's 2 nanometer announcement, and the title was "There's a lot more room," as in Gordon Moore.
Yeah, a lot more. See, you're not apathetic either. Yeah. Well, there's also this funny thing. There's a belief system. When everybody believes technology is moving at this pace and the whole world oriented towards it, because like technology isn't one thing. There's people who figure out how to build transistors. Like, what the process designers do at like Intel or TSMC or Samsung is they use the equipment which can do features, but then the features actually interact. And then there's some really interesting trade-offs between how should this be deposited and etched, and how tall should it be and wide, and what the space. So they're the craftsmen using the tools. So the tools have to be super sharp, and the craftsmen have to be super knowledgeable, right? And that's a complicated play, and there's lots of interaction. And at some level, you can see, because the machines themselves are complicated, you have this little complexity combination where the machine manufacturers are doing different pieces. They don't always coordinate perfectly, or they coordinate through essentially the machine integration guys who design the process. And that's complicated, and that can slow things down, but it's not due to physics fundamentals. Like, we're making good progress on physics fundamentals. And
I put up your, I think I mentioned before, your scaled ML talk, where you have the one that you have in Comic Sans, where you have the printed X, and you say, as time goes on, the way you print the X, because of the laws of physics, and
yeah.
there's still several more steps to go on EUV, and high NA EUV coming in a couple of years. But you mentioned
Well,
X-ray. You mentioned X-ray. What's the timeline for that? It's not even on my
uh,
radar yet.
I'm forgetting what the machines were available for commercial. Some part of typically when a technology that comes along, they use it for like one thing the first
Yeah.
time. Like, when the EUV was first used in DRAMs, it was literally for one step, or maybe
Mm.
two. So I'm trying to remember, 23, 24. It's not that far
Yeah.
away. That means they're already up and running, and people are playing with it. And
Yeah.
and then the wild thing is, when they went from optical light to UV, it was about a 10x reduction in wavelength, right? And so
Mm.
they'd gone to these crazy multi-patterning, interference kind of stuff that you saw those pictures of. And then EUV, they could print direct, but actually they can use the same tricks on EUV. So EUV is going to multi-patterning, I think, in 3 nanometer, and then there's many tricks you can do with that. So yeah, the physics is really interesting. And then, along with the physics, of the optics stuff, and then there's, the purity of the materials, which is super important, and then the temperature control, so things don't go around too much. Like, everywhere you look, there's a, interesting physics problem. And but there's lots to do.
And thousands of different innovations needed.
Yeah,
I recall
but
you saying
there's
at one
literally
point.
hundreds of thousands of people working on it. So, if every group of 10 people does an innovation, there's more than enough innovation bandwidth. So,
So, pivoting to a popular question we had, it's so one of the things that we've noted you doing as you go from company to company is, the topic of building a team. Um, and as you build more teams, we've seen certain people take engineers from a team they've built at a previous company to the next company. Have you got any insights into how you build your teams, and have there been any different approaches at the companies that you worked for on this?
well, the first thing you have to realize is, are you building a team or finding one? So there's a great museum in Venice, the David Museum, In the front of the museum, there's these huge blocks of marble,
Yeah.
20 by 20 by 20. How they move them, I don't know. And the block of marble is sitting there, and Michelangelo could see this beautiful sculpture in it. It was already there, right?
Yeah.
The problem was removing the excess marble. So if you go into a company that's 1,000 employees, I guarantee you there's a good team there. You don't have to hire anybody. We didn't hire anybody. When I was at AMD, I hardly hired anybody. We moved people around, redeployed people, let's say, and but there was plenty of great people there. When I went to
So
Tesla, we had to build a team from scratch because there was nobody at Tesla that was building chips. And I hired people that I knew, but then we hired a bunch of people that I didn't know at some point. And then this is one of those interesting things. If you only hire, I've seen leaders go from one company to another and they bring their 20 people, and then they start trying to reproduce what they had before. And that's a bad idea because 20 people isn't enough to reproduce it. But it alienates, what you want when you build a new team. Ideally you get people you really like, either you just met them or you work with them, but you want some differences in approach and thinking because everybody gets into a local minimum. So the new team has this opportunity to make something new together. And some of that's because, if you had 10 really great teams all working really well, and then you made a new team with one person from each of those teams, that may well be better because they will, reselect which the best ideas were. Because every team has pluses and minuses. And so you have to think about if you're building a team or finding a team, and then what's the dynamic you're trying to create that gives it space for people to have new ideas. And some people get stuck on one idea, and then they work with new people, and all of a sudden they're doing this incredible thing. You think, wow, they're great. They used to be not so great. What happened? Well, they were carrying some idea around that wasn't great. And then they met somebody who challenged them, or the environment forced them, or, whatever, happened. And all of a sudden they're doing a great job. I've seen it happen so many times. Ken Olson at Digital said there's no bad employees, there's just bad employee job matches. And when I was younger, I thought that was stupid. But as I've worked with more people, I've seen it happen so many bloody times that, I've even fired people who went on to be really successful because they weren't doing a good job because they were stuck and emotionally they were committed to something that wasn't working. And the act of moving to a different place freed them up. I don't get thank you notes, but I should.
So how much of that also comes down to sort of company culture? I mean, when you're looking for the person for the right position, or whether you're hiring in for the new position, do you try and get something that goes against the company grain or goes with the company grain? Do you have any tactics here, or is
It really depends on what you're doing. If you're trying to do something really innovative, it's probably mostly against. If you have
right?
a project that's going really well, bringing in an instigator is just going to slow everybody down because you're already doing well. You have to read the group and the environment. And then there are some people who are really good. They're really flexible. They go, on this project, I'm going to fit in and just push. But on the next one, I'm going to, you can see them. They're building their network and team. And on the next project, they're ready to do a pivot. And everybody's willing to work with them. It's like trust is a funny thing, right? If somebody walks up and says, jump off this bridge, you'll be fine. You're like, bullshit. But if you'd already been through a whole bunch of stuff with them and they said, look, trust
Yeah.
me, you jump and you're going to be fine. It's going to suck, but it's going to be fine. You'll do it, right? And teams that trust each other are way more effective than ones that have to do everything with contracts, negotiation, and politics. So
It,
that's probably
it's
one thing. If you're building a team, building or finding a team, when you start seeing people, let's say, doing politics, which means manipulating the environment for their own benefit, they got to go, unless they're the boss. And then, then you have to see if they deliver. Like some people are very political, but they think their political strength comes from delivering.
yeah.
But people randomly in an organization that are political just cause lots of stress.
Do you recommend that sort of early mid-career engineers, they bounce around regularly from project to project just so they don't get stuck in a hole? So it sounds like that seems to be a common thing.
You learn fastest when you're doing something new, working for somebody that knows way more than you. So if
Yeah.
you're relatively early in the career and you're not learning a lot, or the people that you're working for aren't inspiring you, then yeah, you should probably change. Um, so there's some careers where I've seen people bounce around 3 times because they're getting experience and they end up being good at nothing. And they would have been
Ah,
better staying where they were and really getting deep at something. So, creative tension. There's creative tension between those two ideas.
that kind of leads into a good question, actually, because I wanted to ask about you and your mentors, going through your early career. Who did you look up to for leadership, knowledge, skills? Is there anyone you idolize?
Oh yeah, lots of people. Yeah, well, it started out with my parents. Like I was really lucky. My father was an engineer and my mom was super smart, kind of more verbally and linguistically. And the weird thing was when I grew up is I was sort of more like her, thinking wise, but I was dyslexic and I couldn't read.
Mm.
And my father was an engineer. And so I grew up thinking I was like him, but I was actually, intellectually more like my mother. And they were both, smart people. Now they came out of the 50s, and my mom raised, a family, and she didn't start her career as a therapist until later in life. But they were pretty interesting people, and I got that. And then when I first started at Digital, I worked for a guy named Bob Stewart, who was a great computer architect. He did the PDP 1144, 1170, VAX 780, VAX 8800, and the CI interconnect. And somebody said every project that he ever worked on earned $1 billion back when that was a huge number. So I worked for him, and he was great. But there was a half a dozen other really great computer architects there. And while I was at DEC had DEC research labs, and I got to meet guys like Butler Lamson and Chuck Thacker and Joel Helm. And I worked. Nancy Cronenberg was like one of my mentors when I was a little kid, practically, who's one of the chief people in the VMS operating system. And so, that was kind of lucky. Um, so yeah, did I idolize them? Well, they were both daunting and not, because I was a little bit of a, you know, I don't know. I didn't quite
Were you a
realize
hotshot?
who they were at the time. No, I was more a little oblivious to what was going on. You know, like my first week at Digital, well, we got trained on this drawing system called Valid, which is kind of before the Mentor Graphics era. And this guy walked in and he was asking us questions and telling us about hierarchical design. And I explained to him why that was partly a good idea and partly stupid. And so we had like an hour debate about it. And then he walked off and somebody said, "That's Gordon Bell." I said, "Who's that?"
Oh,
He goes, "He's the CTO of Digital."
yeah.
Well, really? Well, he's wrong about half the stuff he just said. I hope I straightened it out. But, I think that's just I'm low in, serotonin activation or something. So, you know, that's more of a mental problem with me than a feature. I think
So would you say you've matured?
not a bit. Uh,
Is that where the fun is?
no, I mean, there's a whole bunch of stuff. When I was young, it was like I get nervous when I gave a talk, or
Mm.
um, like believing. It used to be like I realized I had to understand the people around me better, but I wasn't quite convinced. It was like just rather they, just do the right thing or something. So there's a bunch of stuff that changed. Like I'm really interested in what people think and why they think it, and I have a lot of experience with that. And every once in a while, you can really help debug somebody or get the group to work better. I don't mind giving public talks at all. I just decided that the energy I got from being nervous was fun. So I still remember like walking out on stage at Intel at some conference, like 2,000 people. And it was like I should have been really nervous, but instead I was just really excited about it. And so some of that kind of stuff changed, but that's partly conscious and partly just practice. I'm still really excited about like computer design and stuff. I had a friend of mine's wife said, "What do they put in the water?" I'm like, all you guys ever do is talk about computers. And we're like, "Well, it's really fun, changing the world. It's great."
It also sounds like you spend a lot more time sort of studying the human experience if you're understanding how people think, how people operate, compared to being, mouthing at Gordon
Yeah.
Bell for an
Well,
hour.
it's funny. People occasionally ask me, like I tell people I read books, and you learn a lot from books. Books are fun, by the way. If you know how a book works, somebody lives 20 years and then passionately writes their best ideas, and there's lots of those books, and then you can go on Amazon and find the best ones. Like, it's hilarious, right? Like, really condensed experience in a book written, and you can even select for better books. Like, who knew, right? Um, but I've been reading a lot of books for a long time. Like, it's hard to say, well, read these 4 books and it'll change your life, because sometimes a book will change your life. But reading 1,000 books will change your life. That's for damn sure. And there's so much human experience that's useful. It's like, who knew Shakespeare would be real useful for engineering management, right? But like, what are all those stories? Power politics and devious guys, and the minions doing all the work, and the occasional hero who's saving the day. And it's like, how does that all play out? Like, you wrote all these plays 500 years ago, and it applies to corporate America every single day of the week. So if you don't know Shakespeare or Machiavelli, you don't know nothing.
I think I remember you saying that before you went into your big first management role, you read 20 books about management techniques, and you ended up realizing that you'd read 19 more than anybody else.
Yeah, pretty much. Yeah, I actually contracted with Venkat Rao, who's famous for the Ribbon Farm blog and a few other things, to figure out. So I really liked his thinking about organization from his blog, and he had a little thing at the bottom that says, "Click here to buy me a cup of coffee or get a consulting, or consult with me." So I sent him an email, and so we started yakking, and we spent a lot of time talking before I joined AMD. And he said, "You should read these books," and I did. I thought everybody who's a big management job did that. Nobody
Yeah.
does. It was hilarious. Like, 19 is generous. I read 20 more management books than most managers I've ever read. Or they read some superficial thing like Good to Great, which has some nice stories in it, but it's not that deep a book management wise. You'd be better off reading
Hmm.
Carl Jung than Good to Great if you want to understand management. And
Do, do you find yourself reading more fiction or nonfiction?
as a kid, I read all the nonfiction books, and then my parents had a book club. So when I didn't really learn to read until I was in 4th grade, but somewhere around 7th or 8th grade, I read all the books in the house. So they had John Updike, and John Barth was one of my favorite authors when I was a kid. Um, so there was a whole bunch of stories, and then there's weird ones like, um, shoot, I'm drawing a blank on the name. I'll think of it in a second. Doris Lessing. Doris Lessing wrote a series of science fiction books that were also psychological, you know, in, inquiries. And I read that, and I couldn't believe it. Like, every once in a while, stuff like that kind of blows your mind, and it happened obviously at the right time. But then now I read all kinds of stuff. I like, history and anthropology and psychology and mysticism, and there's so many different things. I've probably read less fiction books in the last 10 years, but when I was younger, I read probably mostly fiction.
I mean, I did get a few comments from the audience because when you are being interviewed by Lex, you said that you read 2 books a week, and you're very adept at quoting from key engineers and futurists and stuff. I'm sure if you started tweeting what books you're reading, you'll get a very large following, a sort of passive Jim Keller book club.
Yeah, that'd be fun. I would say I used to read two books a week. Now I read a lot, but it tends to be blogs and all kinds of crazy stuff. But I've never, I don't know, like, doing Lex is super fun. I don't know that I have the attention span for social media to do anything like that. I'd forget about it for weeks at a time. So it'd be sort of useless.
I'm sure people just want lists, I think. But how do you make sure that you're absorbing what you're reading rather than having your brain diverting about some other problem that you might be worrying about? I mean,
Well, first of all, I don't care at all. I don't really care about that. I know people that read books and are really worried if they're going to remember them, and they spend all this time, highlighting it and analyzing it. I read for interest, right? So what I really remember is like people have to write 250-page books because that's like a publisher rule, like, and it doesn't matter if they have 50 pages of ideas or 500. So you can tell pretty fast. I've read some really good books, only 50 pages because that's all they had. You read 50 pages, you think, wow, it's really great. And the next 50 pages is, it's the same shit, and then you realize, well, he just fleshed it out. No, I wish he just published a shorter book, but, that is what it is. But if the ideas are interesting, that's good. I meditate regularly and then I think about, what I'm thinking about, which is sometimes related to what I'm reading. And then if it's interesting, it gets incorporated. But your brain is this kind of weird thing. You don't actually have access to all the ideas and thoughts and things you've read, but your personality seems to be well informed by it, and I trust that process. So I don't worry that I can't remember somebody's name because their idea may have changed who I was, and I don't remember which book it came from.
Sorry, as long as you passively absorb it at some level.
Yeah, well, there's a combination of passive and active. And I told Lex, like, a lot of times when I'm working on problems, I prep my dreams for it,
Mm.
and it's really useful. Um, and that's a fairly straightforward thing to do. It's you, before you fall asleep, you call up to your mind what you're really working on and thinking about. And then my personal experience is sometimes I really do work on that, and sometimes that's just a problem in the way of what I actually need to think about. And I'll dream about something else, and I'll wake up going, well, one way or the other, it was really interesting. But
So I mean, on the topic of time, I mean, here we are discussing, and you've discussed with Lex, personal health, study, meditation, family, but also how you execute professionally, right? Are you one of these people who only needs 4 hours sleep a night?
I like 7. Well, I don't. Everybody. I added it up one day that my ideal day would have like 34 hours in it. Because I like to work out. I like to mess around with my kids. I like to sleep and eat, and I like to work. I like to read. So I don't know. I just work's the weird one because that can fill in lots of more time than you want to spend on it. But I also really like working, so it's a challenge to kind of tamp it down.
Well, I mean, when there's a deadline, what kind of gets pushed out the way first? Because I mean, you've worked at companies where getting the product out time to market has been a key element of what you're
Yeah.
doing.
I don't know
Is
for
it
about
reading?
the
Is it
last
exercise?
no, for about the last 6 years, the key thing for me is once I have too much to do in some place, I find somebody that wants to do it more than me.
Oh,
Like
right.
like I mostly work on unsolved problems. I was the laziest person at Tesla, as best I could tell. Well, Tesla had a culture of like work 12 hours a day to make it look like you're working, and
Yeah.
no, I worked 9 till 7. Like I wasn't. It was a lot of hours. But I also, I go running at lunch and work out. Yeah, they had a weightlifting room in Deer Creek on the right next to the big machine shop. So I go down there for an hour and work out and eat. So and AMD and Intel, they were big organizations. I had a really good staff. So I'd find myself spending way too much time on presentations or working on some particular thing, and then I'd find some people who wanted to work on it, and I give it to them, and go on vacation.
Or
So
speaking to press people like me and
yeah, yeah,
filling up your time. What's
yeah.
what's your feeling about doing these sorts of press interviews and more sort of marketing and corporate and discussion, which aren't really necessarily related to actually pushing the envelope? It's just talk.
It's not just talk. I worked on some really interesting stuff, so I like to talk about it. Like when I was in Intel, I realized one of the ways to influence the Intel engineers, like everybody thought Moore's law was dead, and I thought, holy crap, Intel's a Moore's law company. Like it would
Yeah.
be really a drag, if your main thing was dead, and I thought it wasn't. So I talked to various people because then they amplified it and debated it and went back inside. And, I reached more people inside Intel by doing external talks. So that was useful to me because, I had a mission to, build faster computers. That's what I like to do. So, and then when like I talk to people, they always bring all kinds of stuff up. And, like the work we do impacts people. Guys like you think really hard about it. You talk to each other, and then I talk to you, and you ask all these questions, and it's kind of stimulating. It's fun. It makes me orient. Like if you can explain something really clearly, you probably know it. Like there's a lot of times you
Hmm.
think you know it, and then you go to explain it, and you're stumbling all around. Like I did some public talks where they were hard to do. Like the talk actually seemed simple, but getting to the simple part, you had to get your ideas out and reorganize them, and then throw out the
Hmm.
BS. And it's a useful thing.
Is
So
that Feynman or Sagan said that if you can't explain a concept to a college at a college level, first year college level, then you don't really understand it.
yeah, that sounds probably like Feynman. He did that really
Yeah,
wild lecture series on physics. That
yeah.
was quite interesting. Feynman's problem is he had such a brilliant intuition for the math that his idea of simple was often not that simple. Like he just see it, you could just tell. So he was like, "Well, I got from here to here by these three leaps." Like he calculated some orbital geometry in like 5 steps, and he was like so excited about how simple it was. But I think he was the only person in the room that thought it was simple. And yeah, he was.
I presume he had the ability to visualize things in his head and manipulate them. Because I remember you saying at one point that when it comes down to circuit level design, that's the sort of thing you can do.
Yeah, I'm much more of a visual thinker. Yeah, if I had one superpower, it's like I feel like I can visualize how a computer actually runs. So when I do performance modeling and stuff like that, I can see the whole thing in my head, and I'm just writing the code down. So I don't, um, which is really useful skill. But I probably partly was born with it, and partly developed it, and partly it's a it's something that came out of my late adult diagnosis of dyslexia.
Yeah, I was going to ask how much of that is nature versus nurture.
Yeah, it's hard. There's this funny thing with super smart people. Often things are so easy for them that they can go a really long way without having to work hard. So I'm
Hmm.
not that smart, fortunately. So persistence and what they call grit is super useful, especially in computer design when lots of stuff takes a lot of tweaking. You have to believe, like you can get there, but a lot of times there's a whole bunch of subtle iterations to do, and practice at that actually really works. So yeah, everybody's a combination. If you don't have any talent, it's pretty hard to get anywhere. But sometimes really talented people don't learn how to work, so they
Hmm.
get stuck with just doing the things that are obvious, not the things that take that persistence through the mess, you know, to the other side.
Also, I guess identifying that talent is critical as well. If you don't know you have it.
Yeah, but on the flip side, you may have enough talent, but you just haven't worked hard, so people give up too soon sometimes. So, but you got to do something you're really interested in, like when people are like struggling, like I don't know if I want to be an engineer in marketing or this or that. It's like, man, what do you like? Like, or especially people that think, well, I want to be an engineer, but my parents or somebody wants me to be a manager. Like, oh my God, you're gonna have a tough life because you're not chasing your dream, you're chasing somebody else's, and the odds of you being excited about somebody else's is low. And if you're not excited, you're not gonna put the energy or learn. So that's a tough loop to be in.
So, I mean, to what extent do you spend your time mentoring others, either inside organizations or externally with previous coworkers or students? Do you ever envision yourself doing something on a more serious basis, like the Jim Keller School of Semiconductor Design?
No, so no, it's funny because I'm mostly mission driven. Like we're going to build Zen, we're going to build autopilot, and then there's people that work for me, and then as soon as they start working for me, I start figuring out who they are, and then some of them are fine, and some of them have big problems that need to be, let's say, dealt with one way or the other. So then, I'll tell them what I want. Sometimes I'll give them some, say, pointed advice. Sometimes I'll do stuff, and you can tell some people are really good at learning by following. And then people later on tell me that I was mentoring them, and I'm thinking, I thought I was kicking your ass. But, it's a funny experience. I have, there's quite a few people that said I impacted their life in some way, but some of it was like, I went after them about their health or diet because I thought they looked, not energized by life, or
Mm.
you can really make really big improvements there, and it's worth doing, by the way. Or they're doing the wrong thing and they're just not excited about it. You can tell they should be doing something else. So they either got to figure out why they're not excited or get excited. And then a lot of people start, fussing with themselves or with other people about their status or something. And the best way to have status is to do something great, and then everybody thinks you're great. Having status by trying to claw your way up is terrible because everybody thinks you're a climber. And, and sometimes they just don't have the confidence or skill to, make the right choice there. So, but it mostly comes out of, being mission driven. Like I do care about people. At least I try to. Um, and then I see the results. I mean, it's really gratifying to get a big complicated project done, and where it was when you started, and then where it was when it was done, and then people when they work on successful things associate the leadership and the team they're working with being part of that. So that's really great. Doesn't always happen, but I
So,
would have a hard time doing that. Just quote mentoring people, because what's the mission? Like, somebody comes to you and says, "I want to get better." Well, better at what? Well, then that's, like, well, I want to be better at, playing violin. Well, it's like, I'm not good at that. Or, whereas I say, hey, we're going to build the world's fastest, autopilot chip. And then everybody working on it needs to get better at doing that. And it turns out 3/4 of their problems are actually personal, not technical. Right.
yeah.
So to get to the autopilot chip, you have to go debug all that stuff, and, there's all kinds of problems, they got health problems and parental childhood problems, and partner problems and workplace problems, and career stall problems, and Jesus, the list is so bloody long. But you have to take them all seriously. Like, it turns out everybody thinks their own problems are really important, right? Like, you may not think their problems are important, but I tell you, they do. They have a list. You ask anybody,
Yeah.
what's your top 5 problems, right? They can probably tell you. Or even weirder, they give you the wrong 5 because you can see the other
Yeah.
5, right? That happens too. But they
They give
definitely
you the
think their
five they
problems.
think you want. They give you the five that they think you want to hear, rather than the actual.
Yeah, or
Yeah.
people have no fly zone, so their biggest problem may be something they don't want to talk about.
Mm.
So, but if you help them solve that, then the project will go better. And then at some point they'll appreciate you. And then they'll say you're a mentor, and you're thinking, yeah, kind of, I don't know.
You mentioned about projects succeeding and people being proud of their products. Do you have a proudest moment of your career? Project accolade, specific moments in time?
Oh, I have there's a whole bunch of them. I
I
worked with
mean,
this woman, Becky Loop at Intel, and we were debugging some quality things. And it turns out there was a whole bunch of layers of stuff. And then, we were going back and forth on how to analyze it, how to present it. And, and I was frustrated with the data and what was going on. And one day she came in with this picture. It was just perfect. And I was like I was really excited for her because she'd, got to the bottom of it. We actually saw line of sight to fix and stuff. But that kind of stuff happens a lot. Like
the
probably thousands.
epiphany.
Yeah. Well, and working with somebody, working with a group of people, going into like it was a mess, and then it got better. The Tesla autopilot thing was wild. Zen's success has been fantastic. Like, everybody thought the AMD team couldn't shoot straight, and I was very intrigued with the possibility of building a really great computer with the team everybody thought was, out of it. Like nobody thought AMD had a great CPU design team. But, the people who built Zen, they had 25, 30 years of, works, history at
Hmm.
AMD. Like that
At
wasn't an
Zen and
outsider thing.
I mean,
So
Mike and Leslie, they've been there for 25, 30
yeah,
years,
yeah.
and
Steve Hale, Suzanne Plummer,
yeah,
you know, yeah.
the
So
lifers.
yeah, they're kind of lifers, but they had done many great projects there. They both had good track. They all had good track records. But what did we do different? Well, we set some really clear goals, and then we reorganized to hit the goals, and we did some really thorough talent, analysis of where we were. There was a couple people who had really checked out because they were frustrated they could never do the right thing, and I
Hmm.
listened to them. Oh Jesus, I have to listen to people. We had this really fun meeting. It was like one of the best experiences of my life. Suzanne called me up and said, people on the Zen team don't believe they can do it. And I said, great. I'll drive to the airport. I was in California. I'll see you there tomorrow morning at 8 o'clock. Make sure you have a big room with lots of whiteboards. And there was like 30 angry people ready to tell me all the reasons why it wouldn't work. So I just wrote them all down on a whiteboard, and we spent 2 days solving them. And it was wild because it started, it was like me defending against, the gang. But people started to jump in, and I was like, whenever possible, somebody would say, I know how we fix that. And I give him the pen, and they get up on the board and explain it, and it worked out really good. But well, the thing was, the honesty of what they did was great. Here are all the problems that we don't know how to solve, and we're putting them all on the table. They didn't like give you two and hold back 10 and say, well, you solved those
Yeah.
two. Against, there was none of that kind of bullshit kind of stuff. They were serious people that had real problems, and they'd been through projects where people said they could solve these problems and couldn't. So they were partly calling me out. It was like I just another bullshitter, and
Hmm.
and I'm not a bullshitter, but I told him, some we can do, some I don't know. But I remember like Mike Clark was there. He was like, we could solve all these problems. Like, and then, I walked out, our thing was pretty good, but then, people walked out of the room feeling okay, but 2 days later, the problems all popped back up. And so you have to just, like how often do you have to go convince somebody? As many times as necessary. And the leadership team on Zen did it, right? That's why they got through it. It wasn't just, me hectoring them from the sidelines. There was lots of people and lots of parts of the team that really said, yeah, I'm willing to really put some energy into this, which is great.
It's at some
So
point I'd love to interview some of them, but AMD keeps them under lock and key from the likes of us.
that's probably smart. Who knows?
Is there somebody in your career that you consider sort of like a silent hero that hasn't got enough credit for the work that they've done?
Well, a person?
Yeah,
Oh, most engineers.
most engineers.
Oh, there's so many of them. It's unbelievable. You know how many people, like engineers, they don't really get it, compared to lawyers who are making like $800 an hour in Silicon Valley, they
Hmm.
engineers so often they just want to be left alone and do their work and, crank out stuff. And there's so many people that are just bloody great. I've talked to people, it's like, this is my 8th generation memory controller, and they're just proud as hell because it works and there's no bugs in it, and the RTL is clean and the comments are perfect. And, they're all over the place. Like I really like
But
engineers. I think,
they don't self promote, or the company doesn't.
yeah, hardly. You know, like engineers are more introverted and you know, conscientious and introverted tend not to be, the people who self promote.
Aren't you a little like me? You've learned how to be more extroverted as you've grown.
Well, I decided I wanted to build bigger projects, and to do that, you have to pretend to be an extrovert and you have to promote yourself because there's a whole bunch of people who are decision makers who don't go, I'm going to do the work to find out who the best architect is. They're going to
Yeah,
say, who is the person that everybody says is the best architect or the loudest or the,
yeah,
capable. So to some level, if you want to succeed above, a principal engineer, you have to understand how to work in the environment of people who play there. And some people are super good at that naturally, so they get pretty high in organizations without much talent. sometimes without much hard work. And, so you're, the group of people, director and above that you have to deal with has way different skill set than most of the engineers. And so if you want to be part of that gang, even if you're an engineer, you have to learn how that rolls. And it's not that complicated. Read Shakespeare, Young, a couple of books, Machiavelli, you can learn a lot from that.
So I know we're coming to time very shortly here, but I want to address a few questions that I think the audience are interested in getting your thoughts on, such
Sure.
as do you care much about Intel versus AMD or Intel versus Apple from your perspective now?
Uh, I worked at all those places. I really like working there. Um, I think, there's always new waves of stuff. I'm really intrigued by the wave of AI startups and the next revolution of computing. So, at the high level, the extent that those are corporate companies with stock prices and boards and, products, they're going to go fight it out how they do it. I care about the engineers, all the companies. I work with lots of people there. I really like them. But no, I don't think that much about them right now in terms of, like, what are they going to do next? Well, we'll see. Apple's always
So,
been so insular about how they do stuff. Like their product touch point is, aluminum box or a glass box.
yeah.
But they've always been kind of a secret society. The engineers are great, but I think they miss out on participation in the wider technical world. Intel and AMD sell components that go into many people's products, so their interface to the public is more, tangible in terms of what the engineers do, right? Because
Yeah.
you buy their chips and you measure their performance and you care about how many PCI Express lanes they have and whether the chip has bugs. So it impacts people more. So I'm interested in what they do, but they're big corporations with a life of their own. So
In terms of processor design, I mean, currently, the EDA tools, there's some amount of automation in there, and advances in AI and machine learning are being expanded into processor design. Do you ever envision a time where an AI model can design a purposeful multi-million device chip that will be unfathomable to human engineers?
yeah, well, so already the complexity of, like, high end, AMD, Intel, Apple chip is almost unfathomable to any one person,
Hmm.
right? But if you actually go down into details today, you can mostly read the RTL or look at the cell libraries and say, I know what they do, right? But if you go look inside a neural network, that's been trained and say, why is this weight 0.001584
Hmm.
nobody
Isn't it?
knows.
Isn't that more data than design though?
Well, here somebody told me this. So scientists traditionally they do a bunch of observations and they go, hey, when I drop a rock, it accelerates like this, and they calculate how fast it accelerates, and then they curve fit and they realize, holy crap, there's this equation, right?
Yeah.
So so physicists for years came up with all these equations, and then when they got to relativity, they had to bend space, and quantum mechanics, they had to introduce probability, but still there's mostly understandable equations. There's phenomena now where there's a phenomena that a machine learning thing can learn, like predict. Physics is some equation, put inputs, equation outputs, right?
Hmm.
Input function output, right? What if there's a black box there where the AI network says inputs, black box of AI outputs, and if you look in the box, you can't tell what it means. Like there's no equation, right? So now you could say, well, that's the design of the neurons is obvious. The little processors, little 4 teraflop computers,
Mm.
you know, but the design of the weights is not obvious, right? And that's where the thing is. Now let's go use an AI computer to go build an AI calculator. What if you go look inside the AI calculator and you can't tell why it's getting? So now don't you understand the weights? You don't understand the math or the
Mm.
circuits underneath them. That's possible.
Yeah.
So now you have two levels of things you don't understand, but what are you designing? You might still be designing the human experience, right? Like
Yeah.
computer designers used to design things with transistors, and now we design things with high-level languages.
Mm.
So those AI things will be building blocks, but it
You'll
is
get
pretty weird that there's going to be parts of science where the function is not intelligible. Like Stephen Wolfram said something really interesting. Like he said, physics. There was physics by explanation. That was Aristotle. 1,500
mm.
years, right? He was
Yeah.
wrong about a whole bunch of stuff. And then there was physics by equation, like Newton,
Mm.
Copernicus, people like that. And he says, this is Stephen Wolfram said, now there's going to be physics by program, right? There's very few programs that you can write in one equation.
Yeah.
Programs are complicated. And he says, why isn't physics like that? Well, in computing world, now we have program by AI, which has no intelligible equations in it or statements. So why isn't physics going to do the same thing? So
So it's going to be those abstraction layers down to the transistor. Eventually, each of them will be replaced by AI, some
yeah, well,
unintelligible black
could
box
be the
AI.
thing that assembles the transistors makes things that we don't even understand as devices.
Yeah.
Like people have been staring at the brain for how many they still can't tell you exactly why the brain does anything.
20
They
watts of
say
fat and salt.
yeah, and they see chemicals go back and forth, and electrical signals move around, and they're finding more stuff, but it's fairly sophisticated.
One of the future aspects of computing is security, and we've had a wake of side channel attacks, potential can of worms, to do with the tricks that we use to make fast computers. To what extent do you approach those security aspects when you're designing silicon these days? Are you
Mm.
proactive? Do you find yourself specifically proactive or reactive?
No, so the market is sort of dictating needs. So the funny thing about security, first of all, is it only has to be secure if somebody cares about it, right? And then for years, security like an operating system was virtual memory. This process, virtual memory, couldn't look in that process, virtual memory.
Hmm.
But the code underneath it in the operating system was so complicated that you could trick the operating system into doing something. So, so they basically you went from security by correct software. Once you couldn't prove the software correct, they started putting additional hardware barriers in there. And now we're building computers where the operating system can't see the data the user has, and vice versa. So
Hmm.
the operating system can never. So we're trying to put these extra boundaries in, but every time you do, you made it a little more complicated. Um, at some level, security worldwide is mostly security by obscurity, right? Like
Yeah.
nobody cares about you in particular because you're just one out of 7 billion people. Like somebody could crack your iPhone, but they mostly don't care about it. And most, it's a funny thing. There's a funny arms race going on about this, but it's definitely kind of incremental. Well, they discovered side channel attacks, and they weren't that hard to fix. But there'll be some other things, and I'm not a security expert. The overhead of building security features is mostly low. The hard part is thinking it out and deciding what to do. And every once in a while, somebody will say something like, "Well, this is secure because the software does X," and I always think, "Yeah, just wait 10 minutes, and the software will get more complicated, which will introduce a gap in it." So there needs to
Yeah.
be real hardware boundaries in there. And there's lots of computers that are secure because they don't talk to anything. Like there's boatloads, places where the computers are either behind such a hard firewall or literally disconnected from anything. So the only physical attacks work, and then they have guards. So yeah, it's going to be interesting, but it's not super high in my thinking. I mostly follow what's going on, and then we'll just do the right thing. But I have no faith in security by software, let's say, because that
Okay.
always kind of grows to the point where it kind of violates its own premises. And, it's happened many times.
You've worked at Tesla, and when you designed a product specifically for Tesla, and you worked at companies who sell products for a wide array of uses. beyond that sort of customer workload analysis, do you consider, the myriad of possibilities of what you're building will be used for, you know, and the ethics behind what they might be used for, or are you just there to solve the problem of building the chip for the purpose?
Well, the funny thing about general purpose computing is it can really be used for anything.
Hmm.
And so the ethics is more is the net good better than the net bad. And for the most part, I think the net good is better than the possible downsides. So, but people do have serious concerns about this. There's all big movement around ethics and AI, and to be honest, the AI capabilities have so far outstripped the thinking around the ethics of that. I don't know what to think about it. Like what the current systems can do is already stripped us bare. Knows what we think and what we want and what we're doing. And the question is, how many people have that? And one reason to build, let's say, a lower cost AI and programmable AI is, I hope, and we're talking to quite a large number of AI software startups that AI hardware and computing is in more people's hands because then you have a little mutual standoff situation as opposed to one winner take all. But the modern tech world, this has been sort of a winners take all, but there's actually literally several dozen very large companies that have you know let's say competitive relationship with each other. So that's kind of complicated. So I think about it some. Um, I don't have anything really good to say besides the net benefit so far has been a positive, and having technology in more people's hands rather than concentrated seems better. But we'll see how it plays out.
Um, you've worked for a number of big personalities, Elon Musk, Steve Jobs, to name two, and it appears you still have strong contact with Elon. Your presence at the Neuralink demo last year with Lex was not unnoticed.
I was invited by somebody in the Neuralink team, by the way. I'm an Elon fan. I wouldn't say I have a lot of contact with him at the moment. So, but yeah, I knew the chip development team at Neuralink. So I went over there to talk to those guys. It was fun.
So you don't stay in touch with Elon, or
I haven't talked to him recently. No.
it was very much professional, not a personal relationship when you worked for Tesla.
Yeah.
Then,
Yeah.
yeah.
Yeah. Mm.
Because I was going to ask that, because Elon's a big believer in cryptocurrency and regularly discusses it,
Uh-huh.
and as it pertains to demands of computing and resources for something that has no intrinsic value. Do you have any opinions as it comes to
No, not
cryptocurrency?
not much. Not really. I mean, humans are really weird where they can put value in something like gold or money or cryptocurrency, and that's a shared belief contract. And what it's based on, as best I can tell, hasn't mattered much. I mean, the thing the crypto guys like is it appears to be out of the hands of some central government. Whether that's true
Yeah.
or not, I couldn't say. And how that's going to impact stuff, I have no idea. But human, group beliefs are really interesting because when you're building things, if you don't have a group belief that makes sense, then you're not going to get anything done. And group beliefs are super powerful, and they move currencies, obviously, politics, companies, technologies, philosophies, self fulfillment. You name it. So that's a super interesting topic, but the details of cryptocurrency I don't care much about, except as a manifestation of some kind of psychological phenomena about group beliefs, which is actually interesting, but it seems to be more of a symptom than a fundamental, or a random example, let's say.
Um, and yeah, for a final question, I wanted to ask you about going beyond silicon. I mean, we've been working on silicon now 50 plus years. This full silicon paradigm has been optimized. Do you ever think about what's going to happen beyond silicon if we ever reach a theoretical limit within our lifetime?
Oh yeah, yeah, yeah. It's like when computers started, with abacuses, right? And then,
Yeah.
mechanical relays, and then vacuum tubes, and then transistors and integrated circuits. And, now the way we build transistors, it's like, what, I don't know, 12th generation transistor. They're amazing. And there's more to do. The optical guys have been actually making some progress because they can direct light through polysilicon and do some really interesting switching things. But that's sort of been, 10 years away for 20
Yeah.
years. But they actually seem to be making progress. The economics of biology, um, it's like 100 million times cheaper to make a complicated molecule than it is to make a transistor. Like, the economics are amazing. Like, once you have something that can replicate proteins, like I know a company that makes proteins for a living, and we did the math, and it was literally 100 million times less capital per molecule than we spend on transistors. Now, when you print transistors, something interesting because they're organized and connected in very sophisticated ways across
Rigid.
vast arrays. But our bodies are self-organizing, and they get the proteins exactly where they need to be. So there's something amazing about that, and there's so much room, as Feynman would say, at the bottom of how chemicals are made and organized and convinced to go a certain way. I was talking to some guys who were looking at doing a quantum computing startup, and they were using lasers to quiet down atoms and hold them in these 2D grids. Super cool. So, I think we've, barely scratched the surface on what's possible. Physics is so complicated and, apparently arbitrary that, who the hell knows what we're going to build out of it. So, yeah, I think about it. And it could be we need AI kind of computation in order to organize the atoms in ways that takes us to that next level. But the possibilities are so unbelievable. It's literally crazy. So yeah, I think about that.
Huh. I mean, it's really great, Jim. I mean, thanks you for spending so much time with me. I think I've got another 20 questions that unfortunately we haven't had time to get to.
Okay, no
Um,
worries.
but good luck. I said it before in the last interview, but again, good luck with Tenstorrent, and look forward to seeing what you come up with.
Okay, great. Hey, good to talk to you again.